Okay, so this is the fourth objective in 2.7, derivatives and rates of change. Rates of change, the calculus of the second interpretation of the derivative, rates of change. Suppose y is a quantity that depends on another quantity, x. Thus y is a function of x, and we write, as we always do, y equals f of x. Now x is changing from x1 to x2. Then the change in x, also called the increment of x, is delta x equals x2 minus x1. And the corresponding change in y is delta y equals f of x2 minus f of x1. The difference quotient, delta y over delta x, change in y over change in x, is f of x2 minus f of x1 all over x2 minus x1. It's called the average rate of change of y with respect to x over the interval x1 to x2 and can be interpreted as the slope of the secant line PQ in figure 8. Slope of the secant line, right? It's the slope of the blue line because it's y2 minus y1 over x2 minus x1. By analogy with velocity, we consider velocity, the second interpretation of the derivative, the first being the slope of the tangent line. We consider the average rate of change over smaller and smaller intervals by letting x2 approach x1, and therefore letting delta x, the change in x, approach 0. The limit of these average rates of change is called the instantaneous rate of change of y with respect to x. At x1 equals x2, which, as in the case of velocity, is interpreted as the slope of the tangent line to the curve y equals f of x at point P with coordinates x1, f of x1. So instantaneous rate of change, the limit as delta x goes to 0 of the difference quotient of delta y over delta x, which is the limit as x2 approaches x1 of the difference quotient f of x2 minus f of x1 all over x2 minus x1. We recognize this limit as being the derivative f prime of x. Okay, and so that's the great achievement here, is that we're able to deal with instantaneous rate of change, okay, the pink line, slope of the pink line, without the limit. Of course, we're not talking about instantaneous. We're just talking about just a difference quotient, just a slope, just a rate of change. So, without these limits, we don't have instantaneous, okay? And so by taking a limit, by using calculus, we are able to figure out the rate of change of some quantity with respect to another at an instant. We know that one interpretation of the derivative f prime of a is as the slope of the tangent line to the curve y equals f of x when x equals a. Slope of the tangent line. We now have a second interpretation. The derivative f prime of a is the instantaneous rate of change of y equals f of x with respect to x when x equals a. That's what f prime of a is. Of course, this could be a velocity, could be instantaneous rate of change of the position function, or it could be some other rate of change. Here's an interesting observation by Stewart. The connection with the first interpretation, slope of the tangent, is that if we sketch the curve y equals f of x, then the instantaneous rate of change of the slope of the tangent line to the curve at the point where x equals a. Okay, so if you sketch the curve y equals f of x, could be velocity, could be some other rate of change, but if you sketch the curve and then get the slope of the tangent, now we're talking about the instantaneous rate of change. This means that the derivative, when the derivative is large and therefore the curve is steep, such as at point P, right? Tangent line is steep here. The y values change rapidly. When the derivative is small, the curve is relatively flat. Tangent line is flat. It's not steep as at point Q. The y values change slowly. In particular, if s equals f of t is the position function of a particle that moves along a straight line, okay? Now that doesn't mean f of t is a linear function. It just means that the particle is moving along a straight line, and then f of t is, not likely to be a straight line. Then f prime of a is the rate of change of the displacement s with respect to time t. In other words, f prime of a is the velocity of the particle at time t equals a. Okay, so we've got f of t, position function, and then we've got f prime, which is the velocity. What's the relationship between velocity and speed? Sometimes they are used interchangeably, but in the Stewart way to talk about things, the speed is of the particle is the absolute value of the velocity. That is f prime of a. So speed can't be negative, but apparently velocity can be negative if you go in the negative direction, if the particle were to go in the negative direction along the line. A manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards, okay, so now we just want to keep this in terms of one dimension, yards. Okay, we don't want to think about length times width. We're just thinking about length, X yards of this fabric, C equals f of x. So here are a couple of questions in this example. What is the meaning of the derivative f prime of x, and what are its units? In practical terms, what does it mean to say that f prime of 1,000 equals 9? Which do you think is greater, f prime of 50 or f prime of 500? What about f prime of 5,000? Okay, so we've got this cost function, and so we've got this cost function, c equals f of x. What's the meaning of the derivative f prime of x? Okay, well, it's going to be a rate of change. Try to understand. Okay, it's going to be an instantaneous rate of change of c, which is f of x, with respect to x. The rate of change, the instantaneous rate of change of cost with respect to the number of yards. That is, f prime of x means the rate of change of the production cost with respect to the number of yards produced. Because, here's just a definition, f prime of x equals the limit as delta x goes to 0 of delta c over delta x, change in c over change of x, as delta x goes to 0. The limits for f prime of x are the same as the units for the difference quotient delta c over delta x. C, that's cost in dollars. X, that's yards. Since delta c is measured in dollars and delta x in yards, as we just said, it follows that for the units for f prime of x are dollars per yard. Okay, so next question. In practical terms, what does it mean to say that f prime of 1,000 equals 9? Okay, after 1,000 yards of fabric have been manufactured, that's x, right? So we're on the 1,000th, or we have just done the 1,000th yard. Okay, the rate at which the production cost is increasing is $9 per yard. Okay, so 8, 9, 9, 10, as we go from 998 yards to 999 yards to 1,000 yards to 1,001. We might be going from, probably we're going downward from, say, $11 per yard to $10 per yard to $9 per yard. Maybe we stay on $9 per yard as we continue to produce yard by yard of fabric. Then maybe we get down to $8 per yard. So at an instant, at that 1,000th yard, okay, I mean, that doesn't mean the machine's stopping at that point, stopping its production, but, at that 1,000th yard, f prime of 1,000 equals 9 means that after 1,000 yards of fabric have been manufactured, the rate at which the production cost is increasing is $9 per yard. When x equals 1,000, c is increasing 9 times as fast as x. 1 yard, $9. Since delta x equals 1, okay, that's how we have to think of an instant in this case. So we're just talking about 1 yard. So now the denominator here is 1. Since delta x equals 1 is small compared with x equals 1,000, we could use the approximation. F prime of 1,000 is approximately equal to delta c over delta x. That's small. It's kind of like taking the limit. Delta c over 1,000, or delta c, and say that the cost of manufacturing the 1,000th yard or the 1,001st is about $9. Why do they say that? The 1,000th yard or the 1,001st? Well, we're thinking about, okay, at an instant, at that 1,000th yard, how much is cost increasing? Okay, yard by yard by yard. Well, if you somehow took a snapshot of the production at 1,000, what would you say? You just did the 1,000th, or what you could expect for the 1,001st yard of production? Probably the latter. Probably the 1,001st is kind of the yard that we're talking about, and production increases $9 from what it was 1 yard ago. In other words, the 1,001st yard is about $9. The cost of manufacturing the 1,001st yard is about $9. C. Which do you think is greater? F prime of 50 or F prime of 500? Okay, and then we'll ask about F prime of 5,000. Rate of change of the cost with respect to the number of yards. 50 or rate of change of cost with respect to the number of yards for at the 500 yard point. Okay, well, this is where some experience can help you if you have any experience in a situation like this. Otherwise, it's not really obvious why the answer is what we think it is. The rate at which the production cost is increasing per yard is probably lower when x equals 500 than when x equals 50. The cost of making the 500th yard is less than the cost of making the 50th yard because of economies of scale. You might not be thinking about economies of scale if you're a 18-year-old freshman and you're not thinking about, you've never really worked in such a place. But economies of scale, okay, and so we get more and more efficient as we go in our production methods. The manufacturer makes more efficient use of the fixed costs of production. So we feel pretty confident that f prime of 50 is going to be greater than f prime of 500. What about f prime of 5,000? But as production expands, the resulting large-scale operation might become inefficient and there might be overtime costs. Now, that's just a might be. If you said that you thought that f prime of 5,000 is greater than f prime of 500 because of economies of scale, it would be hard to argue that. We don't really know the details about this production plant. It is possible that the rate of increase of costs will eventually start to rise. So it may happen that f prime of 5,000 is greater than f prime of 500. Okay, so overtime costs, other things may begin to change the relationship the other way.